In this video, we're going to talk about calorimetry, that is the measurement of energy. Let's get that definition out there. Calorimetry is the process of measuring the amount of heat absorbed or released during a chemical reaction. We're going to get quantitative. We're going to put some numbers to it. Let's recall the law of conservation of energy. The amount of heat energy gained by reacting molecules is going to be equal to the amount of heat lost by the surroundings. And we can flip that. The amount of heat energy lost by the reacting molecules will be equal to the heat energy gained by the surroundings. So if we're talking endothermic or exothermic, the amount of heat energy gained by one thing is going to be equal to the amount of heat lost by the other thing, whether we're talking about the system or the molecules, reacting molecules, or the surroundings or the system. Okay, here's a question. Which has more thermal energy? A cup of coffee at 90 degrees Celsius or a bathtub at 40 degrees Celsius? 90 degrees is like really hot, almost boiling. The bathtub at 40 Celsius is about 100 degrees Fahrenheit. So a nice warm bath. Which one has more thermal energy? I'm not talking about temperature here. I'm talking about energy. The bathtub, even though it's at a lower temperature, it has a much greater mass. There are many, many gallons of water in a bathtub. There's only a fraction of a gallon in a coffee cup. Well, then, if temperature is not the same as thermal energy, how can we measure the amount of thermal energy in a reaction? I mean, the instrument I've got is the thermometer. What else could I need, or what else do I have that I could use? Okay, here's a way to put it. Temperature is how hot or how cold an object is. Heat is the amount of energy transferred to an object. Heat is a flow of thermal energy and always goes from the warmer object to the cooler object. Temperature is a whole different thing. It's how fast the particles in a sample are moving in a given instant. It's not talking about the amount of energy flowing. High temperatures are fast particles. We might recall that from an earlier lesson. All right, so then what does contribute to the amount of heat energy an object has or is receiving or losing potentially? Well, there's a few things. The amount of energy transferred by a chemical reaction depends on its size, how many particles there are. We can measure that with a scale. That's the mass of a sample, usually abbreviated with an M. The change in temperature it experiences. So if it's a big change in temperature, that means there's going to be more heat energy either flowing into the object or leaving the object. We abbreviate that delta T. And then thirdly, there's this other quantity called heat capacity, abbreviated with a C, that is a property inherent to the material itself. Let's talk a little bit about heat capacity, because this one's a little tougher. It's kind of a new concept. Consider this. If I have a stove that's giving off heat energy at a certain rate, and I put an iron frying pan on it, it's going to warm up pretty quickly. If I want to cook an egg quickly, I'm going to use an iron frying pan. Or some kind of, it might be more like a non-stick metal frying pan. If I have a clay pot that I want to put on that same stove, it would be fine to use that, but I'm not going to fry an egg in that because it would take for a really long time to get that heated up. Instead, I'd use the pot for something that I want to bring to temperature really slowly, maybe like a soup that I want to simmer and I want all the flavors to mix together. I'd use an earthen pot or clay ceramic a pot to heat that up. Heat capacity is the amount of energy required to raise or to lower the temperature of a substance. The most common way to express this is something called specific heat capacity, which is the number of joules of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. The units, therefore, would be joules per grams times degree Celsius. Famously, one of the highest specific heat capacities in a substance that we see in everyday life is water. Liquid water has a specific heat capacity that's about 4.18. That's the amount of joules in a calorie. 4.18 joules per grams times degree Celsius. That's very high compared to several other substances. And it's the reason that oceans have a moderating effect on climate. It takes a lot of water, or it takes a lot of energy to raise or to lower the temperature of a body of water. Consider this. Maybe you've experienced this before. Lake Michigan is a fairly large body of water. It's not as big as an ocean, of course, but it is quite a large lake. And in the summertime, you want to go swimming in Lake Michigan, it would probably be best to wait until about July or August to go swimming. At least that's the more comfortable swimming temperatures in the later summer months. And it actually continues to be warm throughout September and even early October, when the air temperature may have cooled down. Air temps precede water temps in seasonal changes. So even if it's like 80 degrees in April, let's say we get a nice hot day in April, you would not, the water in Lake Michigan would not be comfortable to swim in, because the specific heat capacity of water is much higher than that of the air. So the air might be warm, but the water's cold. And similarly, or conversely, in October, maybe the air temp has dropped to like 50 degrees, but the water temp is still pretty comfortable. Different substances have different specific heat capacities that are characteristic of the substance. So notice in this chart, just showing a few common substances, liquid water is by far the biggest. Below that, ice and steam are roughly the same at 2 joules per grams times degree Celsius. And then by the time you get to metals, although there's carbon here, the rest of these are metals, you get numbers far below 1. So aluminum, iron, mercury, carbon's 0.71. Gold and silver are very low in their specific heat capacities. You can use specific heat capacity to identify an unknown substance. In fact, we're going to use an equation in just a moment where we'll calculate the specific heat capacity of a substance. And there's a lab. There's a really cool lab called specific heat capacity of metals that we'll get to do in this class. Okay, so let's put some numbers to this. Here's an equation. Q equals M times C times delta T. Now recall those abbreviations. Q stands for heat energy. As to why they use the letter Q, I'm not sure. It's just everybody seems to pick the letter Q for energy. That's expressed in units called joules. M stands for mass. That's expressed in grams. C, specific heat capacity, expressed in units of joules per grams times degree Celsius. It's kind of a goofy set of units. And delta T stands for change in temperature, which of course is expressed in degrees Celsius. Let's move over to our Jamboard and tackle a problem together. We're going to use this equation. Q equals MC delta T. A 5.63 gram sample of solid gold is heated from 21 degrees Celsius to 32 degrees Celsius. How many joules of energy is required? Notice they give us the specific heat capacity of gold, 0.13 joules per grams times degrees Celsius. Okay, we want to solve for Q because the question says how many joules of energy is required. They give us the mass, 5.63. So where it says M, I'm going to write 5.63. The specific heat capacity is what stands for C. I'm going to write 0.13. And the goofy units, joules per grams times degrees Celsius. And the temperature change. Now, you can do this a couple of ways. You could plug in the equation final temp minus initial temp, but I actually find it helpful to do a side calculation here. I'm going to do the delta T calculation up here. 32 minus 21 equals 11 degrees Celsius. And so where we get delta T in the equation, I'm just going to plug in the 11. Let's follow the units. We have the grams crossing out with grams within the specific heat capacity unit. We have degrees Celsius crossing out with degrees Celsius. The only unit that doesn't cross out is going to be joules. This is perfect. So on our calculator, let's type 5.63 times 0.13 times 11. And we get 8.05 joules of energy. Not so bad. Not so bad. Good luck with your homework.